All right, welcome to Mass and Energy, section 8.4 in your textbook. So, in classical physics, mass and energy are considered separate things. Einstein messed all that up with his equation that said mass and energy were the same thing, just different forms of the same thing. You could think of that as mass has energy, or energy can be converted to mass. It works both ways. All right, so E is whatever energy you're talking about. M is the mass that you're talking about. C is the speed of light, which is a constant as far as we know. And it's about 3 times 10 to the 8th meters per second. So, as you can see from that right off, a little bit of mass converts to a whole lot of energy, right, which is the basis of nuclear reactions, nuclear weapons. That's why such a small bomb does so much damage. So, have to emphasize that this is a result of Einstein's relativistic physics and cannot be arrived at through classical Newtonian physics. Genius that Newton was, he had no clue about this. All right, so of course, another way to think about this is delta M equals delta E over C squared. Right? So a change, energy has a mass. Right? A change in energy produces a change in mass. So just another way of thinking about it. And that's really what there is to it for our purposes. Let's just use this for a minute to get a little bit of information. So we're going to take an example where a neutron, those particles without charge that are relatively dense, that are in the nucleus with the protons, a neutron, turns out, is a little bit heavier than a proton. So a neutron decays into a proton and an electron plus released energy. How much energy is released? Okay, so what we've got is the neutron goes to a proton plus an electron plus. Now, thing is, we know this, and this. We can look those up in a table, right? So any leftover mass had to be turned into energy. So if we look up the mass of a proton, it's this number with, yes, all those digits are significant. And we're keeping, even though it's a ridiculously small particle, we're still keeping kilograms because that's the basic SI unit. Mass of an electron, 9.11 times 10 to the minus 31. Note that a electron is roughly 1/1000th of a proton. The mass of a neutron is 1.674929 times 10 to the minus 27 kilograms. All right, so basically we have one equation and one unknown. This is pretty easy to solve. So the change in mass is going to equal the mass of the neutron minus the mass of the proton minus the mass of the electron. And then once we find that change in mass, we can use Einstein's equation to convert it to a value of energy. So this change in mass is going to equal, well, you just plug these numbers in. I'm not going to write them all out because you could do that as easily as I. You end up with 1.395 times 10 to the minus 30 kilograms. Right, so that's the amount of mass that's changed, that's left over. All right, when a neutron decays into a proton and an electron. That's the unaccounted for mass. So how much energy is that? Well, the energy release then is going to be that change in mass times c squared. So that's 1.395 times 10 to the minus 30 kilograms times because the units have to get squared also to keep the units straight. So the amount of energy released is 1.26 times 10 to the minus 13 joules. Now, that's the amount of energy released in that. So how does this compare to the mass energy of an electron? Okay, now we're using the term mass energy because what we're referring to is how much energy would be released if all that mass of that electron were converted to energy. If you just talk about the energy of an electron, you're getting into the energy levels and that sort of thing. That's not what we're talking about here. All right, so the energy, the mass energy of an electron, all right, and I'm going to designate that like that, is the mass of the electron times c squared. 9.11 times 10 to the minus 31, and that's kilograms, times 3 times 10 to the 8th squared, and you get, when we put it in the same scientific notation, 0.82 times 10 to the minus 13 joules. So in that little reaction of a neutron converting to a proton and an electron, it actually gives off, it releases more energy than almost twice as much energy than you would get from an electron if the electron was totally annihilated and changed completely into energy. So from that point of view, it's a pretty significant amount. Okay? And that's pretty much all we're going to do with modern physics in this class. So that's a wrap up, and next video we're going to deal with power.